Okay, yeah, the event is Postgres without limits, and let's jump right into what that means. Okay, for those of you that perhaps did math in school, I don't know how many of you guys understand what's written on the screen. Raise your hands since we're okay. Great, a bunch of people do. So our idea is to remove limits from Postgres, to push its limits, to give you data without limits in a cloud-native architecture. So that's what it's saying. It's like what we're building is Postgres without limits and for the cloud. So let's jump right into it. Okay, Postgres, like Sudha said, we started this journey about 8 years ago, early 2016, right? And all the people I used to talk to back then, I'd say, Postgres is the future, or Postgres is happening, or Postgres is going to win. Well, it's now fortunate I don't have to justify too much of that. Postgres has won, is winning, it's pretty clear. Everyone is jumping on the Postgres bandwagon, it's becoming the standard API, right? And why is this the case? You are seeing a lot of people pick Postgres for some of its really strong core qualities, right? It's mature and proven. It's got a really extensible ecosystem. It's backed by a very large community, and it's got a ton of things integrated with it. It's very easy to get started, so on and so forth, right? And so we're playing in this overall ecosystem. We're a part of the Postgres ecosystem overall, and the community as well. And we look at our role as extending the limits of Postgres, right? So we are building Postgres for the cloud. Or in other words, if you're building an application that runs in a cloud native architecture, private or public cloud, and you're trying to use Postgres as the database, there's a lot of work you have to do, and we've kind of done that work so you don't have to do it, right? So that's really the nutshell of what it is that we're doing. But to Sudha's point, let's click in a little more on why did that need a new database, right? Like, why couldn't we just take Postgres and run it in the cloud and call it cloud native Postgres? Well, if you take this simple two-dimensional axis, and we did put a limit symbol in there, so you should at least expect a couple of axes in the presentation. So the y-axis is how much of Postgres feature set does a database support, right? Think of this as a tool for you to map, the world of databases, the world of Postgres-compatible databases, and how do you make sense of what's going on, right? The 300 databases that's there in the market. How do you make sense of them? So on the y-axis is what level of Postgres compatibility does a database have? And the x-axis is how cloud native is its design? How inherently cloud native is that database designed to be, right? And so for purposes of simplicity, we just call it low, medium, high, right? Low being you take standard Postgres and run it in the cloud, that'd be low, right? And you start making it durable, it starts to get medium, and you truly run it in a cloud native manner, it starts to go to high. Now, the interesting thing here is that there's a line, right? There's a line for the Postgres compatibility dimension above which you start reusing the Postgres query execution engine. And at that point, you're inheriting all of the Postgres innovation, right? You're not working hard to keep up with it, you're inheriting it. I think the key point here is this line, this PG innovation threshold line, keeps moving to the top. It keeps moving up with time because the world is innovating on Postgres. And equally, there is another line, right? Like this is the point on the x-axis after which the architecture of the database actually truly becomes cloud native, right? It's capable of doing shared nothing, built-in replication, high availability, so on, right? So that line moves to the right, right? Because industry never stays still, so these lines keep moving. More Postgres innovation, more cloud native innovation, right? These just keep happening. And as a database that came relatively new to the scene, only 8 years old, like in 2016, we wanted to sit at the spot where we kind of take the Postgres innovation and bring it into the cloud native innovation or the distributed architecture innovation, right? So that's kind of where we sit. And if you take some examples of different databases that sit on different sides, you kind of see Postgres is the best Postgres, no questions asked. And by the way, the simple answer in the transactional world to, there's 300 databases, it's insanely crowded, like why build another database? Well, like the simple answer is there's actually only 4 or 5 databases. There's MySQL, there's Postgres, there's Oracle, there's SQL Server, and perhaps DB2, right? Those are the only 5 databases. So if anyone's building a database that's even ANSI SQL compliant, but doesn't quite fall into one of these 4, it's considered a new database. It's not really an option. No one's picking it because it's too complicated to learn yet another database, right? The NoSQL world, of course, works quite differently, right? So if you look at it, like, we look at our position as bringing everything in Postgres to the best of cloud native, right? And so we're trying to bridge the two worlds, the world where you're trying to come from Postgres alone and the world that's trying to come from distributed SQL alone, and put them both together. Okay. So we've been doing this for eight plus years. We picked the Postgres API like back in end of 2015, right? So we've been watching the space way before Postgres was a thing, and this is kind of our simple spin on what we're building on top of Postgres, right? We're making it distributed and cloud native, so to give it resilience, scalability, built-in replication, all of that stuff. So truly make it work for cloud environments. The second one is to make it enterprise grade, which means give it its observability, ability to do high, DR and disaster recovery, and better performance and performance monitoring, security, et cetera, et cetera. And the third thing we're doing is, if you take a traditional database like Postgres and put it in the cloud or in Kubernetes, we're at KubeCon. So if you just put it in Kubernetes, it's not really cloud native Postgres, because it's not about where your database runs. It's about the value of the data you're unlocking in the cloud native architecture. In fact, arguably, if you take a traditional database and put it in a cloud native infrastructure environment like a public cloud or Kubernetes, you're actually going to have worse performance and more cost, right? And more operational headaches, right? But if you architect it right, it really gives you the value, right? And so that's the last part, which is about architecting it truly to work as a database as a service, or truly for unlocking the potential of data in cloud. So that brings us to the question, right, of what really these things are, and we'll look at it in a second. But before we jump in, here are some new product announcements from us that are making this journey quite exciting. Right? If you ask the question, there's already Postgres. What are we doing to it in order to make it distributed and cloud native, to make it truly a citizen of cloud, to make it a database that unlocks the power of data in the cloud? Right. The first thing is to make sure it runs exactly like Postgres. So if you have an application running on Postgres, you should be able to get to YugabyteDB with very little change or no change at all, right? And automatically unlock resilience and some of those properties, right? The second big thing is that in the cloud, it's all about scaling quickly. It's about perhaps replicating across regions for your disaster recovery purposes. It's about multi-nodes and failover. So your cost-based optimizer, the way Postgres executes queries and the way it accesses data may become insufficient, right? Because it always assumes the data is local, and that may not be the case in cloud environments, right? You need to replicate data for redundancy. You need to move data around and processing around for purposes of scaling and so on. So adaptive cost-based optimizer is the second thing. And the third thing is, smart data distribution. So, probably everyone here, I don't know, anybody here have a thought on what they think is the biggest pitfall of a distributed database? Like, well, we're in person, so we might as well ask some questions, right? So any takers, no wrong answers. Sorry? Synchronization. So, or in other words, the time taken to synchronize, or latency, right? So if you move, you have to synchronize. If you're distributed, if you're single node, you don't have to synchronize. Thank you. And that means it takes effort and time, which means your performance and latency are not necessarily as good. So the third piece is smart data distribution, where can we judiciously think about where we need to distribute data and where we don't. Some places you need scale and you can distribute. Some places you don't need to do that. So those are the three things that we're announcing as a new product announcement. Now, a little bit of detail on each of these. So we are right now, we're rebuilding the entire storage, data access, and data processing layer while keeping the query processing layer the same as Postgres. So by looking at how many of the Postgres unit tests and regression tests and features we can run right now, that's at about 91%. But our aim is to go to 100%, right? So the aim is to be Postgres, but built for the cloud. Of course, newer versions of Postgres bring in newer features, and the cloud native innovations require enhancements or newer features added on top of what Postgres has. So those are things we're continuing to add, right? The second thing is, how adaptive can we be? right? So there are a lot of Postgres applications that run that don't need scale, right? Or that assume no scale because all of the data is local. If you start spreading out the data, it takes longer to go fetch a piece of data. And so when you're operating on that piece of data, it actually becomes slower, right? And so the application then sees higher latencies for some of their queries, and that doesn't look too good, right? So here, we're trying to give a dial where we say, we can match Postgres, and then go from there to scaling it. So match it for smaller data sets, and then figure out at what point a user or an application really needs scale, and then start doing the sharding, auto sharding, and distribution and replication. The third bit is around how smart can we be with respect to keeping all of the data, less sharded and distributed, thereby eliminating latencies and performance overheads, versus you need the scale, so do shard them. So like, for example, in a database that has about, say, 100 tables, you might only need 2 tables that are large to be sharded, and the remaining 98 can stay non-sharded but replicated, right? That gives you the best performance whenever you hit queries for the 98 tables that are of mid to small size, and you can get the best performance by distributing data and writing your queries appropriately for the 2 large tables, right? As opposed to having to do all 100 tables that are scaled out, which is what traditional distributed SQL does, or all 100 tables that are not sharded and scaled out, which is what traditional Postgres does. So you can live in this dynamic world of figuring out your scaling needs on the fly. All right, so this is a quick demo of whatever it is that I've been talking about. And so in this demo, Brett will actually take an application from traditional Postgres and move it to YugabyteDB. And we have an open source tool that actually introspects what Postgres is doing in order to support the application and figure out how to move it to YugabyteDB. All right, so without further ado, let's take a look.
Hey, in this presentation, I'm going to show how to execute a migration from Postgres to YugabyteDB using YugabyteDB Voyager. Let's dive right into it. For sake of demonstration, I'm going to be migrating the popular open source community platform named Discourse. I have Discourse running locally on my machine with an admin user and a thread that I have created. All this data is being stored in a Postgres instance, which is running locally on my machine in Docker. I also have a YugabyteDB instance running in Docker, but this is not being pointed to from our application because we have not yet migrated any of the schema or data. But here we can see that we have a migrations tab, which will be populated as we begin running YugabyteDB Voyager commands. So why don't we start running some commands in YugabyteDB Voyager to start kicking off this process. Before exporting the schema and data, it's helpful to generate a migration assessment. This assessment will analyze the source database to provide any potential schema changes that might be necessary, as well as providing recommendations on data distribution and cluster sizing. So we can generate this assessment by using the YB-Voyager assess migration command. And in doing so, the report will be output in JSON and HTML formats. But as I mentioned, this report will also be shown in the YugabyteD UI if you choose to view it there as well. So we can go over to this UI. Previously, no migrations were available. But now we can see that the migration assessment report has been populated, showing that the complexity of this migration for Discourse is low. And we only have 2 manual refactoring steps that have been flagged at this stage of the process. So 2 indexes will need to be refactored for use on YugabyteDB. So let's go ahead and export our schema and continue on with this process. Now we're ready to move forward with exporting and analyzing our schema before then importing it to YugabyteDB. So similar to our assess migration command, we're providing an export directory on our machine where all of this data will be exported. And we're providing the details for our source database. I've just chosen to store them all as environment variables on my machine. So this will be a very quick export of the schema, and then we can analyze this schema. Let's go ahead and analyze the schema that we just exported, running the analyze schema command and setting the output format to HTML. This will generate an HTML file for this report, but we can also view it in the YugabyteDB UI. So let's go over to this UI and check out the schema migration tab. Here we're seeing two suggestions and errors. We're seeing that we have two indexes that use a gist index, which is not supported by YugabyteDB. And we have GitHub issues that are linked as well. So in order to fix this issue, I'm going to remove these two indexes from the schema in my export directory. So then we can successfully import to YugabyteDB. After that slight schema modification in our export directory, we're ready to export the data from our database. So let's run the export data command of the YB Voyager CLI. This will take just a moment, so I'm going to fast forward the recording. Here we can see all of the tables that had data exported as well as their corresponding row counts. So let's now import our schema to YugabyteDB and subsequently import the data and cut over our application. Let's run the import schema command of the YB Voyager CLI to import the schema from our export directory to our YugabyteDB instance running in Docker. We can go ahead and do this, and then we will run the import data command when this completes. This is going to take a few minutes because we have quite a number of tables and indexes that need to be run on our database. After a few minutes, our schema import has completed and we can begin our data import. So let's do that now by running the import data command on YB Voyager. This should only take a minute or so because we don't have a lot of data in our Postgres instance. After this is completed, we can point our application to YugabyteDB and show that we have feature parity between running on Postgres and YugabyteDB. So I'll fast forward when this finishes and we can go check out the application. With our schema and data migrated to YugabyteDB, I've set the database connection details in the Discourse application to point to Yugabyte. Now in running our application, we can see the thread that I had created previously while pointing to Postgres, and I'm able to log in as the same admin user that was created previously, showing that our application has in fact been migrated successfully. To further illustrate this point, I'm going to go into the Yugabyte shell in order to query for our users. We can see that the YugabyteDB admin user has in fact been migrated to YugabyteDB. So that concludes my offline migration from Postgres to YugabyteDB. Of course, if you'd like any more additional details on the steps that I've outlined, or those for executing a live migration, check out our documentation. Thanks.
All right, so yeah, thanks, Brett. So folks, this was just a quick snippet of some of the things that the Voyager Copilot does. It helps you modernize from an application running on Postgres to make it ready for the cloud by suggesting places where it can introspect and look at what are the tables that are being accessed heavily, what are the tables that are growing a lot, and suggestions for which tables need to get sharded, which tables don't, and a layout plan in order for you to move your applications effectively from a traditional architecture to a cloud native architecture, right? So do check it out. It's completely open source, and give us feedback. But net, right? If you're taking Postgres to the cloud, you have to deal with all of these details about how you're going to refactor your applications, which tables need to get sharded, which queries need to get rewritten. It's just a part of the journey, right? And so there is work that needs to be done on top of Postgres in order to achieve that. Folks might opt manual sharding, a variety of different ways to do it. And this is what we are doing and facilitating and making simpler with YugabyteDB, right? Some of the ways in which So that's just an overview of, how we can move. But, you may ask the question, so what exactly is happening? Like, what are some of these ways in which YugabyteDB is actually transcending the limits of Postgres and helping expand the range of Postgres itself, right? So the first one, I think these are 4 things we're going to talk about in the rest of this presentation with examples, with anecdotes and so on. So the first one is around always on resilience and disaster recovery. So how do you make sure that your services are never interrupted? The second one is operations and data protection. How do you make sure that you have the best of that, like especially in a world where outages cause a lot of issues, there's more and more applications being deployed, and the burden of having to run all this and secure it is actually huge. Right. The third thing is built-in scalability. It's also interesting to note that these applications need scale, right? Whether it's transactions per second, data set size, or even connections, right? So we're going to talk about all of those. And lastly, about security and security operations. How can we make that simpler, right, in the world of Postgres and cloud-native data? So without further ado, let's jump into each of these 4. So the first one is resilience and DR. Right? In resilience and DR, like the first thing when you talk about resilience is it's the ability of a system to recover from a failure, right? So when there's an outage, you have to make sure it's still running. The user doesn't perceive an outage, right? And this is becoming super critical. Like resilience is becoming extremely critical in cloud native systems because we as consumers are taught to think of brands as how well their service is run. It's almost a proxy, right? So there may be a company that's doing, let's say, financial transaction processing, right? Now you install their app and you're trying to use it. Like it could be a bank, it could be like a trading system, whatever it is. If their app keeps going down frequently, well, you're going to be thinking like, well, if their app doesn't run that well, they're probably not going to be that good at handling my money, which may not be true at all. But that's the impression the consumers get, right? It's the same with an e-commerce company. It's the same. So it's now become a core competency for brands to make sure everything runs, right? And unfortunately, when you go cloud native, you have exposed yourself to a lot of failures because cloud native systems have failures as the norm, right? Because it's cheaper, it's commodity hardware, there's more things running on it. Like if it's a public cloud, it's got a lot of VMs, a lot of components, right? So customers expect everything to be always on. Nations are starting to digitize, which means like, there's been certain exchange of services and the payment is digital, right? If that infrastructure doesn't work, well, there's going to be a revolution on the streets because someone's not getting paid for doing work and that's never fun, right? And brand reputation requires uptime. So ultimately, resilience is becoming super critical, right? And just to put it from the other perspective, there are a lot of failures when it comes to cloud native architecture. So this is just public clouds, and for the US versus global trend, and based on the number of major outages, these are major network outages, these are not small. The number of smaller outages is a whole order of magnitude higher, right? There's transient outages, a few seconds long, there's like a few minute level outages, there's like major outages across regions. So these are things that we cannot as people go and fix any longer because the scale of operations is too high and the number of outages is too many. The cost of downtime is going up too. So this is just a report on, it's 3.4 billion is the total cost of recovering from outage. And that's just for all the companies running on AWS, right? In US. So, this is for a day of outage, right? So it's starting to creep up there, right? It doesn't matter which cloud, private or public, and it's not anybody's fault because these are massive systems and it's the way it is, right? This is the way that's why the business is of building reliable systems on top of unreliable underpinnings, right? And that's really what we're trying to do. So modern applications need resilience built into Postgres because if you layer it on top, it's going to be too complicated. It's going to be too onerous. It's not going to work as well, right? So when you think about it from that perspective, you have different kinds of failures. You have infrastructure failures like nodes and disks and all of that failing. You have entire regions and data centers going out. You have failures which are not quite failures. It's just degradation in performance. It works, but not well enough. So it's bad enough for users to complain or not use the service, but not good enough, not bad enough to where you can actually detect it as a clean outage. So there's all these cases that you have to deal with, right? And that requires us to think of resilience as a group of things, not just like something went down, am I running, right? It's not that. It's not about somebody goes and fixes it when something goes wrong. It doesn't work like that anymore, right? So from that perspective, like, some of the things we do at Yugabyte, we allow clusters to have a different form of resilience inside a region and let you pick your form of resilience based on the trade-offs you want to accomplish across regions, right? And this is super critical because traditional databases had only one way to do resilience: replicate it to a replica and fail over, right? But with the percentage, the probability of these failures going up so high, and you could have like a 1-minute failure. What would you do with a 1-minute failure? Do you do a full failover or not? Do you rebuild or not? Like, so after a while, this starts to accrue a lot of operational overhead, and the user, like the end users, the consumers that see this actually get a bad experience, right? So these are some of the things we architect for to make sure that you get the best resilience both inside a region and across regions, and build it from within into the database as opposed to on top. Right? So this is a quick workflow of a disaster recovery workflow where we're going to take down one region, and in many cases you have to be ready for it, just like a fire drill. You don't have the fire, but you need to know what to do when the fire hits. So similarly, what happens if you have to take down a data center? Do you know you're ready? What really would happen, right? Here's an example of a workflow.
Thanks, Karthik. For our first solution, DR orchestration, I'm super excited to share with you an early look at our upcoming built-in and simplified workflow to make configuring and testing your DR strategy incredibly easy. Let's jump in. So here's our database cluster in Oregon. It's for the same TradeX app that we saw in an earlier demo. We're going to set up replication to a new cluster in Virginia and then conduct a failover. Here we choose our Virginia cluster as our DR replica. Then let's choose to replicate the TradeX database. We need to next set up bootstrapping, which is the process of seeding an initial copy of the database over to our target cluster in Virginia. Now, we do want an alert if our lag between the two clusters exceeds 1 second, because we don't want to lose more than 1 second of data in case of a total failure. The DR stream is in progress being set up. The database continues running. There is no downtime, but some operator actions, such as config changes and version upgrades, those are disallowed. And voila, we're done. Replication is now active. We are now replicating data from the DR primary. Meanwhile, the DR replica is receiving data and is indeed able to handle database reads. While everything is going great, let's fast forward a month or two and bam, there's an emergency. Users, the CIO, everyone is in crisis. We see this error message in the DR stream, and we even learn from elsewhere that Oregon itself is down. So it's a big company decision, really. We as a team decide we need to fail over now. And this is not a graceful failover. That was the orange. This is a immediate failover from that action menu that will, in fact, orphan some data on the Oregon cluster. We need to do that to get our app running again. We trigger the failover, and behind the scenes, we marked that Oregon universe as failed. We've promoted also behind the scenes the Virginia cluster to be the new DR primary, and we now allow reads and writes. As a result, our app can recover, resume, and we've achieved business continuity. Well, that went by really fast. With a few mouse clicks, we failed over, and we are working to make it that simple in both our UI and the API. Easy and integrated DR orchestration with async replication powered by YugabyteDB X Cluster. It's our new DR solution. Passing it back to you, Karthik.
All right, thanks, Yushin. So a couple of interesting things to note. TradeX is another open source application that runs on Postgres, so we were able to move it over quite easily, very similar to the first demo. The second thing of interest is if you notice the total data loss lag, it was 39 milliseconds, right? So one of the things that a distributed database lets you do is it lets you push data from multiple nodes in the source cluster to multiple nodes in the destination cluster thereby keeping your lag really small. So you can actually push it much, much faster, right? So this not only reduces the probability or the amount of data loss, you can also re-architect this in a different way where you can make it a synchronous replicated cluster to make that data loss exactly zero, right? And the failover automatic. So there's a few choices when it comes to designing your DR the way you want it, right? Okay, so
Thanks, Karthik. For our
Okay, so let's look at the next bucket. The next bucket is around gray failures. So failures that are there, failures that are not there. And, there's a bunch of classes that contribute to gray failures, like, performance degradation or like, random delays, your disks like not working well and thereby losing data. You have, memory thrashing, machines not working well, so on and so forth. So you have a whole bunch of this class of failures that, ultimately need to get detected, because the user doesn't care that it was a hard to find failure. The end user cares that, the service is either working or it's not, right? And so as a database that is built for cloud native architectures, becomes a part of what we do to detect them, what we do to remediate against them. So this becomes an important class of things to look at as well. They're very subtle. They're very hard to reproduce. It always works on the developer machine. And in fact, in this case, it also works on the machines of the people that are testing it. It's just super difficult to even reproduce these in real world scenarios, especially in public clouds, because you don't know when it happens, right? So we look at this across the base of all users using us and look at how do we detect them and how do we remediate them, right? This is like one of the examples, like where, you have like when you use EBS disks, right? You could have gray outs sometimes on AWS. And once again, it's not to say they did a bad job. No, they absolutely have done a great job. But when you run very large scale systems with a lot of virtualization, with a lot of infrastructure driven code at the scale at which they do, these things are bound to happen. And these are protection and detection and protection mechanisms that we have to put in, right? And so these are some of the ways at which, we push the limits of what Postgres can do. Here's a real example. Like I said, there'll be examples here. There's innumerable examples that I cannot quote, but here's one that I can. So there's a customer of ours, Plume, that had that was running billions of operations per day, like a lot of stuff going on. And one of the zones on AWS actually went down, right? Like this was in the Europe region. And, typically as these things go, it takes some time for people to get in, to find out, to ascertain that there's an outage before you can put out a notice. So, we were able to notice the alerts, the system was able to auto reconfigure itself, and the folks at the Plume side were also able to notice that there's an elevated latency followed by everything settling down, even way before AWS was able to put out the notice. It was like a couple of hours or an hour before even the notice was put out, because it does take time for people to respond to ascertain it is a large scale failure and to acknowledge it. And we were able to ride the whole thing out, because it took a day to resolve all of the systems. So that's the point here. It just was more to look at things in order to make sure everything is okay and running, rather than having to proactively deal with it as an emergency situation, because you get woken up in the middle of the night and, oh my God, what's going on, and so on and so forth, right? It's never easy to do that. And if you repeat that too many times, well, most likely everyone's going to leave on vacation, because it's not a fun job. So, right. So, okay. There's a session today from Vita Group about how they're using their electronic health records and how they're building it for the Catalan government and for the people of Catalan. So I think do take a look, do attend the session. It's an interesting session. It's going to talk a lot about resilience and scale, right? So they have 10 million citizens, and they are using Kubernetes as well, and they are using YugabyteDB as a Postgres-based cloud-native database. Okay, so we started with this, right? And I think the point is this is precisely what we do, right? Like we are building Postgres for the cloud. Okay, the second big bucket is around operational downtime and data protection. And I'm going to go a little fast here because these are things we understand, but there are nuances. And so I'm just going to point out the nuances. Everybody here would know it, right? Raise of hands who doesn't know this is important. So, okay, so I'm guessing everybody knows this is important. All right, so backups, point in time recovery. So if bad data gets written, you can roll back, upgrades, rolling upgrades, downgrades. If your database upgrade wasn't good, let me go back to my previous version. These are all important things. But let me point out the nuances. It's great to have backups. Everybody has backups until the backups start taking too long. And if you've configured it to take 24-hour backup every day and your backup takes longer than 24 hours, that's a problem, right? You're not going to ever catch up with the backups. It's going to fall behind. So it's important not just to do backups, but to maybe do them with the parallelism and with the scale that kind of ensures that it happens in a timely manner and actually achieves your data protection objectives. Similarly, point-in-time recovery, right? It's good to have them, but it cannot be a brain surgery if you're trying to move your database back. It has to be API backed. You have to be able to say, go back 10 minutes, go back 2 hours, get it very quickly done, right? If there's a lot of data movement, especially with scale, that's going to be a problem. Rollback, right? So this is something that Postgres doesn't support. Like upgrades and downgrades across major versions are not really a thing in Postgres. Like you deal with it. So you go do a blue green and go figure it out, right? And so you figure out compatibility between major versions. But as a database that always wants to keep running, we are able to upgrade one machine at a time. So we drain the all the connections from a given machine. We upgrade it and go to the next and the next and the next. Right. And lastly, when you think about de-risking even more, you want to have blue-green deployments where you have, one region with one version of the software, another region or deployment with another version of the software, not just database, the entire application stack, right? So you can deploy the blue and then you put a green and you upgrade your green. If it's great, you switch over to green and then upgrade your blue, right? So you should be able to do this fairly painlessly because there's a ton of services where you have to do this, right? So this is, I guess I should have spoken to this slide, but this is the green to blue, the switchover, right? How you do the actual upgrades in a safe manner while keeping both running. And the cloud allows you to spin up a whole cluster, run it for like a couple of days, make sure everything is okay, and then take down the old cluster or, switch back and take down the new cluster, however you want to do it, right? So these are things that, are made possible with a cloud native database. Right? And for operational uptime, right, these are things you got to do all the time. Non-destructive upgrades, OS patching, machine SKUs, like a whole bunch of stuff. In just the 6 years we've been around as a company, the cloud providers have changed, machine types and improved the generations of machines, only about 6 to 7 times, right? So that's once per year minimum, right? And so you have to constantly keep upgrading these machines, and it cannot be like a difficult job to do every single time. So this is what we do that we know of, because there's a lot of customers that do it without even telling us. That's the number of upgrades. We do over 1,000 upgrades a year. We do about 2,000 OS operating system upgrades and security patches every year, and about 395 cert rotations, right? In about a 12-month to a little over 12-month period, right? So without enough operational rigor around this, this is going to be difficult to do. Okay, so here's an example of operating at scale, right? So General Motors, the car company, is building a smart vehicle platform, and we are actually the database underpinning all of their data. So like if you want to do, open your car from your cell phone, for example, or you do an emergency roadside assistance call, all of that goes to eventually a database, but also an application stack. And that always has to be on, irrespective of, no one likes to say, sorry, your emergency call got dropped because we were upgrading the database. Is never a good reason, right? So anyway, so this thing always has to keep running. Today there's a talk about Rakuten and how they're deploying a petabyte scale YugabyteDB database natively on Kubernetes. So do catch that. They're running a lot of their critical systems in there too. Okay, the last section is around scalability and connection scaling. And again, people understand what this is, so I'm going to go right through this. And I'm told we're a little short on time, so I might skip the demo for this one. But anyways, this is what planning looks like. You have your 8 or 10 applications, and you think those 2 applications are going to go big. That's what happens in practice. Something completely different gets a lot bigger, and you have to deal with it, right? And now, how do you deal with it? It's going to be a fire drill. It's going to take away many months from your roadmap. No one's happy at the end of it because you dealt with it. It was successful, great, you built it. Now you deal with the success, right? So if you don't want the success to actually become a pain point, like, in a manner of speaking, then you need to be able to scale effortlessly. And there's a lot of talk about vertical scale and horizontal scale. It's not that. It's really, can you do it without the application knowing it? It's seamless. And can you do it really quickly at times? So this is what scale looks like. A lot of people say, how much scale do you really need? Here's some real examples. Core banking. We have systems that have been tested for 1.2 billion total users and about 100 million users per bank, right? And 102,000 business transactions per second, right? If you look at the market data, the middle section, like it was really about lowering the total cost of ownership to simplify the architecture to be able to move fast. And of course, we talked about GM, but that was 3 million operations per second, like, and at 10 times faster scalability, right? So there's a whole lot of ways to look at scale, right? And these are some of them. And here's an example that I'm going to talk about. Like, so we are the database that does identity and authentication for the Paramount Plus streaming app. Right. So earlier this year, Paramount hosted the Super Bowl, which is one of the largest, online events, and there's a bunch of events since that's been pretty big. And we were one of the, very proud to be a very boring part of their infrastructure that just worked because, the 2 hours leading to the Super Bowl or any of these kind of events, like you have Grammys, you have Oscars, you have Champions League, any of these, right? To pick your poison. But the 2 hours leading to it is absolutely nail biting if you're an infrastructure provider because everybody on earth just logs in to make sure they can log in. And then 10 minutes later, they log in because the game started. And then they log in for the halftime because the ads are interesting. And then there's a Taylor Swift show. And then the last 20 minutes of the game. And then the post-game show. And each one is a massive spike, right? So you're not enjoying Super Bowl if you're doing this. But, we were happy to be a very boring piece of this whole thing. Okay, this just says that there's a ton of users, and so other times it's not just about TPS and data set size; it's about connections. And those of you that know Postgres would not like to hear Postgres and connections in the same sentence because it's usually not a positive thing, right? But here are the things we're doing inside YugabyteDB natively, right? So we're making connections faster. You're making more connections per core and consistency of throughput for irrespective of the number of connections. So, we're building in connection manager into the database. So 5 to 20 times faster establishment of connections when you have a burst of connections. 5x more connections core for core against Postgres, right? And the third thing is irrespective of the number of connections, your transactions per second remains consistent, right? So these are some of the things. This is the innovation that we've put in where we've taken a connection manager, we've improved it to put sticky connection handling and authentication pass through and all of that stuff natively and inside, Postgres/YugabyteDB. Okay, so there's a demo for how autoscaling looks like, which in the interest of time, I am going to skip, right? So, this is going to be running on our booth at KubeCon. So, you can see workloads go up, go down. You can see the Kubernetes cluster autoscale with it. And so do catch it, right? Okay. The last bit is around security. And again, we don't think of security as something we need to build for, but it turns out it is increasingly with more and more of our data becoming digital. So these are some of the stats about just ransomware. One attack vector, right? And human error and environment misconfiguration are the top two problems, right? And this is something that, we are building as a foundational capability in YugabyteDB. So we're building for sensitive mission critical transactional data, and our deployment, it comes out in code as secure by default and irrespective of where it runs, right? Like in your VPC, in ours, wherever it is, right? So these are some of the things we do with our YugabyteDB Aeon, our managed service, to be able to ensure, right, when it comes out. On top of that, like our fully managed service, ton of compliances, which make sure we adhere to the strictest standards of security as well. Okay, so what's coming? I mean, we should have started with AI, Gen AI, but let's at least finish with it. So we are, this is nothing that we're doing. This is what the Postgres community is doing. They're innovating a ton on Gen AI, PG Vector, its performance, and so on. And what we're really doing is to innovate on top of the innovation, like I said at the beginning of the presentation, to make the Gen AI indexes highly resilient, highly scalable, highly integrated. So it's easier to build Gen AI applications that are usually pretty resource hungry. You don't need specialized databases or a complex setup. You can do it all in a single place, scale when you need to, scale back down when you don't. So net, we're resilience and scale. Enhanced PG Compat is what we announced. Multi-tenancy is coming soon. And after that will be the serverless, the really bursty workloads, right? Is something that we'll look at. There's a ton of interesting sessions throughout the day. Do catch them, right? So there's a lot of live workshops, building Gen AI applications workshops. There's like things about real world data modeling and RAG workflows. There's a lot of people talking about different verticals, financial vertical, scaling payment processing. There's some on the automotive and logistics. So there's a whole bunch of interesting sessions. Do catch them. Most importantly, don't forget to enjoy DSS. It's Distributed SQL Summit. It's actually a good forum for talking about all your cloud native data or infrastructure architecture challenges. It's just interesting. Make the connections. A lot of people in similar walks of the industry, similar journeys. And with that, I'm super happy to welcome Jake from Netscope on the table to the stage to actually talk about what they do in terms of data in the cloud.